Hey, Honors Chem, here's a quick little video to help you identify types of chemical reactions. Okay, we are in Lesson 8. This is section or chapter 8.3, pages 234 to 238, types of chemical reactions. Notice that I have 5 written down. Different textbooks describe the names of these reactions a little bit differently, so I have a few in parentheses here. The first chemical reaction that we're going to discuss is synthesis. Your textbook actually calls it a combination reaction. They mean the same thing. I'll have examples for each one of these 5. Number 2 is a decomposition reaction. Number 3 is a single replacement, also known as a single displacement. Same thing. Number 4 is a double replacement or a double displacement. Number 5 is combustion. Let's take a look at a synthesis reaction. Okay, the first reaction type is a synthesis or combination reaction. Your book calls it a combination reaction. I usually use the word synthesis. They mean the same thing. Here is the model that I wrote out for you. You have 2 reactants, 2 chemicals. Reactant A, this is the model. Reactant A plus reactant B will yield, there's your yield arrow, a more complex compound, chemical AB. So what I have below are 3 examples that you can refer back to. These reactants can be single elements, they can be molecules, they can be compounds. I have down here, I'll show you this. Uh, Basically, you have 2 chemicals, 2 reactants that are going to make a more complex molecule, more complex compound. So let's look at the first one. Solid magnesium, that's a single element, plus oxygen gas, it's a single element, but it's a diatomic molecule, will yield magnesium oxide. A plus B yields AB. However, I figured I'd go back and review balancing because this equation is not balanced. Notice 1 on the left, magnesium, 1 on the right, magnesium, but the oxygens are not balanced. So I need to put a 2 in front of this um, compound and put a 2 in front of the magnesium. Next one, nitrogen gas plus hydrogen gas yields NH3, which is ammonia. Chemical A plus chemical B yields AB, but it's not balanced, so let's make sure we balance it. 3 and 2, we need to make that 6, so that's going to be a 2 there. 2 times 3 is 6. 3 times 2, hydrogens is 6, and the nitrogens are all set now. The last example has 2 compounds still coming together to form a more complex molecule or a more complex compound. Magnesium oxide in its solid state plus carbon dioxide gas, chemical A plus chemical B or reactant A plus reactant B yields AB. They come together. This is already balanced. It's all a 1-to-1 ratio. Okay, reaction number 2 is called a decomposition reaction. I want you to think of it as the opposite of a synthesis or combination reaction. All textbooks use this particular word, decomposition. Here is the model. What you're going to see in order for you to realize that it's a decomposition reaction when you're identifying them, you will see a particular chemical. In this case, it's going to be a compound, chemical AB, and boom, you only have 1 reactant, and then you have the yield arrow. So a decomposition reaction has a single reactant breaking down, decomposing into 2 products that are either single elements or simpler compounds. AB yields A plus B. Here are 2 examples. I balanced these because I didn't want to waste time. 2HGO, mercury 2 oxide. It's a solid, but boom, right after that you have the yield arrow. The delta is some sort of chemical change that is happening. But again, what you should look at is a single reactant, then the yield arrow, and you have 2 or more products. mercury, and oxygen gas. Down here we have calcium carbonate, CaCO3, single reactant. Then you have your yield arrow breaking down into not single elements like you have in this reaction, but two compounds. It doesn't matter if it's breaking down into elements or compounds, but you have a single reactant breaking down into two or more products. Next, we have single replacement, also known as single displacement reactions. Here is the model. A, which is going to be a single element, plus BC, which is a compound, yields AC plus B. If this doesn't make sense to you, the classic single replacement model, the classic single replacement reaction, describes two elements that are similar. In this case, I want you to think of element A being a metal, and I want you to think of element B also being a metal. These are alike. These are similar. They behave the same way. They want to lose electrons. Element C, let's say it's a non-metal. Well, sometimes you have metals that are more reactive than others. So in this case, metal A is more reactive than metal B, and it wants to bond with non-metal C. So what's going to happen is one element is going to bump off. It's going to replace another to form a compound with that other element that's not really similar to it. So in this particular case, element A is going to bump off or knock off element B, and it's going to form AC as a compound on the product side, and element B, which was part of a compound originally, is now by itself. I think these examples will help. This first equation describes exactly what I've shown here. You have a metal, zinc, and you have hydrochloric acid, HCl. Now, I understand that hydrogen is not a metal, but it does act like one because it only has one valence electron. So what's going to happen is zinc is going to bump off hydrogen, and this is right in your textbook. These are two examples right from your book. Zinc is going to bump off hydrogen to form a compound with the chlorine. These are already balanced for you. So now you have A plus BC, and on the product side, you're going to have AC, zinc and the chlorine bonded together. It makes ZnCl2, zinc chloride, and you have hydrogen gas all by itself over here, where originally it was part of a compound. Sometimes you can get two nonmetals that will act the same way and bump each other off. So here's another example from the book. Notice that chlorine gas, it's a nonmetal, and you have a compound here, potassium bromide. Potassium is a metal. Bromine, or the bromide ion, is a nonmetal. These two, where my fingers are, those two are alike. Those two are similar. One's going to bump the other off, but it's not going to be a metal action this time. The chlorine is going to bump off the bromine. So what's going to happen is you will get KCl. We always write the metals first. Don't forget that. Potassium chloride, KCl, and bromine has gotten bumped off, and it's all by itself. Single replacement or displacement. In a double replacement or double displacement reaction, you have two compounds, typically ionic compounds, that are going to swap partners. Again, remember that an ionic compound has a positive ion bonded with a negative ion, a positive cation, negative anion. Same thing with this particular compound here. And they're going to swap partners. So if you are unsure of why the product side is written like this, let's talk about it real quick. Positive, negative, cation, anion. The two also here, positive, a cation, negative anion. The two cations are never going to meet up. They're not going to want to bond together. So what happens is, and remember we always write the cation first, A is going to want to bond with D, and the metal, or I should say the cation C is going to want to bond with B. So they swap partners, and the examples, the balanced equation examples will show this. AB plus CD yields AD plus Cb. Here's the first example. Barium, which is a metal, barium chloride. Metal, nonmetal, cation, anion. Look at this next reactant. Sodium, cation, positively charged, metal. Sulfate, the sulfate, polyatomic anion. That's the negatively charged ion in this particular case. Here is A, here is B, here is C, here is D. They're going to swap partners. The barium is now going to be bonded with the sulfate, and the sodium is going to be bonded with the chlorine or the chloride ion. Two different reactants, two different products. Here's another example. This is a good one. We'll see this when we talk about acids and bases. Here is sodium hydroxide. There's your cation, the sodium. The OH minus is your anion. NaOH plus HCl. This is hydrochloric acid. You have an acid and a base, two different reactants. They're going to swap partners. Now, here's the cool part. This this hydrogen, which acts like a metal, is going to bond with the OH. And we're not going to call it HOH. We're going to call it H2O. My marker is dying. But this is a neutralization reaction. It's still a double replacement or double displacement with a base reacting with an acid to form water and a particular salt, in this case, sodium chloride. One more, we have combustion. Last type of reaction is called a combustion reaction. Combustion reactions are actually pretty easy to identify. Here's the model. This is going to look a little different than the AB plus CD stuff. In this particular reaction, this type of reaction, you have a carbon-based compound, usually bonded with hydrogen. Sometimes it can be with oxygen, but notice I have CXHY, some sort of carbon-based compound. And in order for something to combust, it has to be burning. And on planet Earth, it's going to burn in the presence of oxygen. We know that things light on fire and they stay lit on fire if we continually add oxygen. Carbon-based compound plus O2 are the two reactants. On the product side, we have the same two products every single time. I want to reiterate that. Your clue, your tip that you're looking at a combustion reaction is something burning in the presence of oxygen, and you always get carbon dioxide gas as well as water vapor. Here are two examples. I might actually talk about a couple more. The first example is CH4 gas, methane gas. It's natural gas, plus 2O2 burning in the presence of oxygen. By the way, this reaction is already balanced. Will yield CO2 gas plus H2O gas. I should have put that in parentheses. Plus energy, usually in the form of heat and light. We get energy by burning these chemicals and getting these two products. Here is another example of a combustion reaction. C3H8. Notice it's got carbon in it and hydrogen in it. Not the same carbon-based compound. By the way, this is propane. This is the stuff that I cook my meat on the grill with in the tank. Some of you might heat your houses with propane. Propane gas, C3H8 plus 5O2, 5 oxygen molecules. Still, it's O2. You get the same two products, carbon dioxide and water, just like up here. Okay, that is a clue that you're looking at a combustion reaction. I'm going to pause it. I'm going to put one more on the board for you. One more quick example of a combustion reaction. I wrote that incorrect. C6H12O6, which is called glucose, plus 6O2 oxygen gas. Notice you have the same two products here, carbon dioxide and water. This is what's going on inside your bodies right now. It's a combustion reaction, just like we burn natural gas or propane or a candle. This is just a slow burn of the sugars that we eat. We breathe in oxygen gas to allow that sugar to burn, And as we exhale, we're getting rid of carbon dioxide gas as well as water vapor. And those are the types of chemical reactions.